Thank you. Welcome back. And we have a wonderful final presentation of the day. I know a lot of you did a lot of hobbies over COVID, and I'm sure many of you are very productive. Well, our next speaker was very productive, developing two interesting devices that will be highly useful for Mars exploration, but also helpful for medical science here on Earth as additional, hopefully not too many additional pandemics come out. Larry Kuznetz, I'm going to read a quote on the website from astronaut Charlie Carmada. He said, Dr. Lawrence Kuznetz was on the console of mission control during Apollo 11 and introduced the space shuttle to the American people on the Johnny Carson Show Tonight Show. A little redundant there. He also helped build Space Shuttle Columbia, demonstrated that water could remain liquid on the surface of Mars and that native extremophiles could survive there. He's a pioneer in STEM education and is currently building the first spacesuit for Mars and the PPE Q-suit based on it that could stop the next pandemic. Dr. Kuznetz holds graduate degrees from UC Berkeley and Columbia University. He has 8 U.S. patents, and he is the author of the sci-fi novel about Earth-Mars dysphoria, an autobiography of the space shuttle, and a spacesuit user's manual for kids from 9 to 90. So ladies and gentlemen, Dr. Larry Kuznetz. Sorry, a little awkward reading off my phone.
Hi there, Chris. How are you all? Hi, everybody. Pleasure to be here. Can you all hear me? Yeah. Yes. Okay, so wanted to start this off. First slide. Hello, first slide. Okay. One, back one. One, back one. Okay, great. So the topic, what I'm going to do is unveil something to you that has not been seen before, a radically different EVA spacesuit for Mars. Most people are familiar with spacesuits. So I wanted to tell you that what you are about to see and what you are about to hear begins and ends with this. This is Article 11 of the 1967 Outer Space Treaty. It declares all spacefaring nations must avoid harmful contamination from the introduction of extraterrestrial matter. What that means is there will be no forward contamination, if it's preventable, from outbound planetary missions, and there will be no backwards contamination from planetary missions returning to Earth. And this holds for people, rovers, sample returns, anything that we send out that comes back here. This has been signed by all spacefaring nations. It is in force today. I happen to know a little bit about this because the very first job I ever had at NASA, which seemed comical at the time, was preventing moon bugs from coming back from the moon on Apollo 11. Now, my job was to design a filter in the, a filter in the post-landing ventilation system. That's the command module returning. This is the ventilation system up at the top, so that if any moon bugs had been inadvertently picked up, they would be filtered and stopped from getting out to destroy us and infect us. What was sort of comical about it is you notice that the hatch is open on the Columbia command module. And that just is an indication of how laughable the idea was at the time. But NASA had to go through the motions because of Article 11. As the years run by, NASA has taken this and applied it to all of its planetary efforts, planetary protection efforts. And you see there was what in the center up at the top was called the biological isolation garment that the Apollo astronauts wore when they stepped out of the command module. By then, of course, anything that might have been in there was already out. And then you see the mobile quarantine facility where Neil, Buzz, and Mike Collins were in an Airstream trailer that was quarantined, and they all came back to this building, which I happened to work in for a number of years, the Lunar Receiving Laboratory, where for 14 days they were kept under severe quarantine to make sure that there was nothing coming back from the moon that could contaminate the rest of us. And that included burning all their clothes. The building was kept at a lower pressure, so air would come in, it wouldn't get out. All these measures were taken. And as the years went by, this philosophy was moved forward to robotic missions. So here you see Perseverance being prepared, and you see everybody involved in Perseverance's preparation is wearing clean room suits in a place that's kept as sterile as possible, right? So these are the kinds of efforts that were made. It's not that NASA did not try, but planetary protection is hard, especially when it comes to spacesuits. So here you see an image taken of Pete Conrad during Apollo 12 on the surface of the moon, surrounded by an aura of stuff coming off of his spacesuit from the sublimator that's being dumped on the surface of the moon. This is how spacesuits work. The same system is in force exactly today. Sublimation for cooling, coming off the top of the suit. Everything comes out. You don't know where it's going, but of course we're not on the moon, we're not on Mars, we're in low Earth orbit. So there you go. So all of that got me very interested, having been weaned on this kind of stuff. And I said, well, maybe there's a way to deal with this. So this is what led to what's called the MarsSuit project. And in my career back and forth, I've taught at UC Berkeley different classes. So this was one where we came up with a class called the MarsSuit project to develop and build a spacesuit specifically for Mars, because everybody knows, or should know, that Mars could be a lot more biologically active than the moon. And most important of all, that spacesuit had to conform to Article 11 to protect planet Earth, right? Now, in the process of doing this and learning how to do this, we came up with something called a Hypernet paradigm. Now, I want to show you what that is, because it's very unusual. Hypernet paradigm is a project-based learning through enhanced internet networking. That's the long words of what it means. But what it really is, universities, industry, government, public work together. Anybody can use it. Skills, all kinds of skills are usable in this project. So how does it work? The first thing that happens is you take a project and you break it up into pieces. It doesn't matter if it's a Mars spacesuit. It doesn't matter if it's a way to approach cancer cures. It doesn't. The many different approaches you can use for this. But in the particular case of the Mars spacesuit, we broke it up into elements. You see all these elements here: pressurization, thermal control, materials, utilization of planetary resources, science, life sciences, center display, power, all these things. And you break them up into as many as you can, and then you combine them to simplify the thing. And you combine them into what we called work packages. So here you see 1, 2, 3, 4, 5, 6, 7, 8 work packages that encompass everything that we saw. And then you go out on the internet and you recruit talent pools. And these talent pools can come from anywhere. In the beginning, they came from UC Berkeley and Stanford and Rhode Island School of Design. But as this project grew, more people joined the talent pool. And this is how the whole thing worked. We set up an organization. So over here, so we're all clear on this, are the work packages that I just showed you: helmet, torso, portable life support system, gloves, materials, software, logistics, and also a steering committee. Those were the work packages. Then you take the talent pool and you form them into teams, mostly by passion. You ask a group of people, what would you like to work on? What's most interesting to you? Which one would you be most interested in? And you form this team under each one. And it's a multidisciplinary team of universities, industry, individuals. Anybody can be in a talent team assigned to that project. And then you give them a starting point. This is what we know about this project. We're going to give you the starting point, and we're going to let you run with it. Use your imagination. Come up with anything you want, and you do that. And at the end of a semester or a period of time, you just tell us what you learned. You write a report. You give us a piece of equipment. Whatever you do, give it to us. And so here's what happens. Each of these teams, then, you see, come down here, and they make a report or a trade study or a piece of hardware. But the key is this. Once that happens, you'll notice this line going up to the top, the feedback loop line. It goes right to the top, to the first team, and they give it out for peer review to experts. They give it to people in industry, people at NASA, people who know this business. and they give it a critique. They give it a reality check. Once they give it a reality check, it's fed back into an interactive design environment website. Many of you have used these things. They have whiteboards, they have chat rooms, they have all this stuff to communicate. Oh, that's what that steering wheel means. And it comes right back into the system for round 2. And this round 2 evolves round 3. And round 3 evolves round 4. And the beauty of this is you can take this organization approach more than once. If you're a high school student, you can take it in college. If you're a freshman, you can take it as a sophomore. For a sophomore, you could become a team leader. If you're a team leader, you could do it in graduate school. Maybe you want to do a PhD, but the whole time you're doing it, you're meeting people in the industry and you're learning about what it takes to do this kind of thing. So you can take this course, in the early days it was a course, multiple times for credit, because the beauty of it is you don't reinvent the wheel. You're always building on the last part. So that's what's important about it. It's an iterative, evolving project. So the very first time we did this was a Stanford University UC project team effort that resulted in this book, Spacesuits and Life Support Systems for the Exploration of Mars. It was filed as a postdoctoral thesis. It is available on Amazon.com today. Many people say this is the Bible of Mars spacesuit design. You can find it if you want and look at it. Second iteration that took place.
Long envisioned a colony of humans living and working on Mars.
This is a CNN report that was done.
No.
Okay. These students are learning what it takes to travel to and live on the red planet. 25 years ago, this would have been a course in science fiction. Now, undergraduates majoring in everything from political science, astrophysics, computer science, engineering, astronomy, molecular biology have come together for this class at the University of California, Berkeley.
Yes. Okay, tune them down like this.
Students share a passion.
Great. I think my generation should go, for sure.
I've always wanted to be an astronaut since I was really little.
And I, for one, would love to see humans go to Mars.
You want to go?
Yeah, I'd like to go if they could send me.
Really? You want to go? How many of you would want to go to Mars?
No, everybody wants to go.
Good to know now. The class is split into groups. Each takes on a problem that even NASA has yet to solve. What to wear on Mars. According to these students, it's not the 350-pound spacesuit that astronauts wear now.
This is an incredible suit. It's really a work of art. Unfortunately, this art will not work on Mars. First off, it's way too heavy.
Because there's gravity on Mars. Students designed this 30-pound suit instead. The outer layer protects against UV rays and sub-freezing temperatures.
Mars is a place that is very, very cold. It's a lot like Earth. It has seasons, it has gravity, it has air pressure, much less gravity, much less air pressure, but it's also very, very cold.
The suit.
So that, by the way, is Dr. Shana Gifford. 20 years later, she's giving a talk in this very conference. So I don't know if she's in the audience. Shana, are you there? But if you're not, everybody will shake your hand tomorrow. So she's now a medical doctor. That's great. Following that, early on, that was 2012, we had 3rd, 4th, 5th, 6th iterations. You see other classes working on this. And what they started to look at in detail was NASA designs from 1969 to 2022. And then they looked at industry designs of spacesuits. So here you see, you've probably seen some of these spacesuits, and you say, how cool looking, how slick looking. You've got to remember, they are not EVA spacesuits, half of them. They are certainly not meant for Mars. They're designed to wear inside a vehicle. So here you see all of those. So I just wanted to show you this, because this is just a small sampling of the people and teams that have contributed to this over the years. You see astronauts, you see individuals, you university teams, government, industry advisors. You see if you look at a geography of the United States, you see it's from all over the place that come in, because you have the ability to do this without geographical bounds, using interactive website design environments such as the EPIC challenge that NASA had for projects like this. So after all of this, these teams concluded the suits that you just saw might look pretty, but they're either too heavy, too expensive, too complicated, won't function on Mars, and more to the point, provide no planetary protection, right? So what happened then, they also violate the holy grail of Mars spacesuit design. I call it the holy grail. Gravity, thermal control, survivability. A 300-plus pound spacesuit might work on the moon, which has 16% gravity, Wear it on Mars, you'll be flattened and barely able to move in 38% gravity. Significant torso puncture, all of the oxygen in your suit would be gone, and you would be gone in less than 60 seconds if you had a significant puncture. And finally, planetary protection, conformance with Article 11 is ignored and non-existent. So, how do you deal with this? Fortunately, Mars can help. How? It has seasons, weather, and diversity. It has soil and topography like Earth. It has an atmosphere and atmospheric pressure. It has all the things we have, and you can leverage its environment. Would you wear a bikini in the Arctic? Ask yourself. Would you wear a ski jacket in Miami? You have a planet that helps you, so you don't have to do that. All those EVA suits are designed like thermos bottles. They don't care if it's hot, cold, no pressure, high pressure. They're big, bulky things that weigh a ton because that's how they're designed. They don't have the ability to use the planet they're on. Use it. So under the microscope of all these things and all these iterations, a solution converged. And we call it the integrated two-gas open-loop flow-through system pressurized by the Martian environment. Think about that. Pressurized by the Martian environment. Distinguishing features. Planetary protection. It has separated systems by a patented neck dam that keeps the helmet and the torso completely separate. Carbon dioxide in the atmosphere of Mars is used to pressurize the torso. Oxygen is used to pressurize the helmet. You emphasize what we call KISS in the business. Keep it simple, stupid. And by doing that, you can lop off over half the weight of those 300-pound spacesuits, because you don't need pumps and fans and all the equipment necessary, big tanks, to be completely isolated from where you are. Puncture protection, radiation mitigation, modular evolution capable. It will grow with where the places you go and with materials come on and all new technology comes. You can embody that into this. So how does this work? Just check out this little animation so you can see what's really going on here. Hopefully. So there's a compressor right here that's bringing in the Mars atmosphere. It's pressurizing the suit, and it's coming out a relief valve, and it's removing heat, carbon dioxide, sweat, toxicity, everything that all the heavy equipment does. It's just being blown through. But if you look at the helmet is a completely different system, being pressurized by oxygen. That's the point of the design. There's some other things I could tell you about, but not right now. So now what I wanted to skip to a little bit is this radical design came because of the Hypernet paradigm. And the Hypernet paradigm is an example of the way science works. Science works in sometimes strange, magical ways, occasionally discovering unexpected benefits. Things that the people who are doing the research never intended it to do. For instance, penicillin, the microwave, Velcro, the Big Bang, Teflon, vulcanized rubber, Coca-Cola, radioactivity, cornflakes, gunpowder, strikeable matches, the color mauve. These things and many more were discovered accidentally, right? Well, NASA has taken this to the limit. Here are some examples of the list that's come from NASA technology, studying something else. Exterior paint, epoxy for dental crowns, GPS, ultra insulators, new methods of protective clothing for extreme environments, crop management, hurricane storm weather tracking, Earth observations, telecommunications, of course, energy, water, accident prevention, fatality reduction in cars and planes, because NASA has an agreement with NASCAR, the stock car racing organization, to take all the data that they get from these horrendous crashes, put it in supercomputers, and design equipment that will withstand these horrible crashes. Anybody who's interested in Formula One, if you've ever seen people walk away from crashes in Formula One, you cannot imagine how that could possibly be. All that technology goes into your car and goes into your airplane and goes into Orion and all the spacecraft that we're building. So this is a magical connection. So in the middle of the pandemic, a light bulb moment occurred. Could by building a spacesuit for Mars that provided planetary protection, could that lead to a pathogen prevention PPE suit on Earth that would protect you against the next pandemic, which could be far, far worse than anything we've ever seen? Is that a possibility? And as a result of that, in a very short period of time, because the technology had been so developed in the Mars spacesuit, came the MQ suit. MQ stands for mobile quarantine. Keep that in mind, mobile quarantine. So the idea was escaping microbes from the Apollo suit led to the Mars suit, which had filters to counteract that, led to the MQ suit, and which is going through revisions and production right now, pre-production right now. So it's an example of migrating one technology to another. To be more specific, in the Mars suit, we have viral filters at the suit inlet compressor, viral filters at the suit outlet relief valve. And in the MQ suit, we have pretty much the same idea. Everything coming in is filtered, everything going out is filtered, double filtered. Now, I'll talk about that in a little bit more in a minute. So the specific design features for this is that nothing can get in and nothing can get out of this MQ suit. Not only that, there is no opening. There are no openings in the front of this suit. There's no exposure. There's no holes. There's no anything. It has a helmet. It's all isolated and contained. And when do you catch a virus? When do you get sick in dealing with another person? When you're facing them, when you're talking to them, when you're bending over to them in a hospital as a doctor or a care provider. This is when that happens, not when you've got your back to them. So again, you'll see what I'm about to talk to and how this works in a moment. But I wanted to finally list all the different features that have been extrapolated from the Mars spacesuit to the MQ suit. Mobile quarantine, no restrictions, no isolation, no sheltering, masks not required. You're under quarantine while you walk around. Healthcare provider, schools, emergency PPE, transportation, hotels, individuals, military, hazmat, identifying positive individuals because you'll be in this suit, and when you're in the suit, after 14 days, you will or will not develop symptoms. That identifies you. That can be isolated from the rest of the crowd. 1 year filter life. The super HEPA filters built into this have a 1 year filter life. They are reusable. They are sterilizable. They are not one-time only throwaways. They are lightweight. They're inexpensive. Projected cost less than $150. And most important of all is something we call ROAR. ROAR stands for Rapid Outbreak Response. Let me show you how that works. When an outbreak is identified, a new outbreak of a new virus or something that's even worse than anything we know, as soon as it's identified, within a radius of X is yet to be identified, call it 10 kilometers, there will be 500 suits deployed within that radius within 10 hours of that outbreak. Everybody in that radius will don these suits. It will contain the spread from ever getting out. That's what ROR stands for. And the ability to deliver 500 of these suits in a short period of time in identifying an area that is confirmed to have the initial outbreak is key to this. And that's ultimately the business model. So there's a lot going on here, obviously. So the plan going forward of both of these suits, what we call the M33, MarsSuit M33 for be on Mars, walking around with it by 2033, the latest. And the MQ1 is mobile quarantine 1. You see here we have our timeline ahead, and it's very aggressive. Low pressure testing has been completed. High pressure testing will be completed by June. Addition of communication sensor, addition of suit compressors to dry the air in. Portable life support system addition and checkout, and preliminary design review by June of next year. Software, math models, qualification tests at sea level of June of 624. And then finally, the big guy is you take the spacesuit, you put it in a Mars environment under Mars pressure, under all those conditions, and you do a qualification test, and finally flight certification by the 1st of 2026. Anybody planning to go to Mars will have this available by the 1st of 2026. As for the MQ suit, we don't have that kind of worry. It's right now in pre-production. Pre-production has been completed, and certification with the FDA comes next and other national health services, you have to pass a whole bunch of tests to go through certification before you're allowed to sell and dispense to the public. So that's where that stands. So I wanted to show you a little bit of snapshots of a preliminary test of the MarsSuit early. Oops, I had a problem there. And here's what the mobile quarantine suit looks like. So a little bit of testing here. No, that's not working. I wanted to give you, we've been approached by Prada, the fashion house. And Prada says, look, we can take this MQ suit and we can fashion the heck out of it. We can make it so slick. People are going to go out and bang the doors down it. If it only costs $150, we're in, right? So, gosh, I want to introduce our startup company called Planetary Protech, and there's myself. And rather than talk about this, I really wanted to finish off with this. We have a credo at NASA that I grew up with. It's still there. Let your reach exceed your grasp. Always reach further beyond what you think you can. And that's what makes a dream come alive. So to show you how this dream came alive after all of this time, I would like to introduce you to our team, if you guys would be good enough to come on out. Okay, so let me run through some of the things you're about to see. So Elizabeth just put a yellow, what we call SOP, secondary oxygen pack, emergency bottle of air, which is in every spacesuit. There's always an emergency supply. So Elizabeth and Eugene are safety officers. So they're here for safety purposes, right? And the red bottle that you see, if you turn it around, so I don't know if you can all read this, but that red bottle is filled with carbon dioxide. That is the Martian atmosphere, 95% of it. So just to give you an idea, we're not on Mars, so we can't pump the Mars atmosphere into the suit, but we can certainly pressurize the suit with the Mars atmosphere that we brought with us. So with that as a starting point, we're going to have Cameron actually take you on an experiment. If you would, Cameron.
So the Mars atmosphere, using a compressor that's typically inside the backpack. The Mars atmosphere is compressed and blown into the suit below the neck down. You see I have a neck down. So the suit from the neck down is filled with Mars atmosphere CO2. And the helmet portion is filled from my backpack an oxygen supply. So I breathe 100% oxygen inside the helmet. Helmet pressure is kept slightly higher than suit pressure, preventing any CO2 from migrating upwards. Let's do that right now. If you give me a little bit of CO2. Now we're going to flow it through here, and we're going to monitor, and you're going to see down here, this CO2 monitor, the reading in parts per million is going to peg out at about 6,000. It's showing you that this is fully CO2 pressurized underneath the neck. And then the upper part of the suit, there you go. So now the lower part of my suit, and I'm getting pressurized, is CO2. And now I'm going to turn on my oxygen supply, put the helmet on. There we go. We used quite a bit of our oxygen during our testing this morning, so we'll see how long of that have. But I'm going to put this on and then show you some exercises.
Now keep in mind that this suit is being pressurized at low pressure mode for about 1 psi. But the suit is pressurized. I don't know if you could see it being pressurized. Yeah, I don't think we can hear you through your mic.
I'm just going to show you some exercises.
Oh, yeah, you can hear his mic. So what he's going to exercise. Okay. You keep in mind the suit is pressurized.
Now here we are. Gene, if you can follow me, we're going to walk on the surface. We've started to include mobility at pressure comparable to the Apollo program.
Now, I want you to understand, this suit, as he's wearing it, it's 75 pounds.
I am the regulator of pressure. Later, we will use algorithms to control the pressure controller. So the size of the suit side.
That's your mic.
Put that here, it works. Or here. Thank you. We still got the good CO2 numbers on the bottom. And then on the top you're seeing, that's my helmet CO2, which is not too bad. That's because I'm breathing my oxygen supply from my backpack. And we're demonstrating that the suit CO2 is managed below the neck ridge. And inside my helmet, 100% oxygen. Perfectly healthy.
So I want to elaborate on what I started to say before. This suit, as you're looking at it, is about 75 pounds. It does not have a rebreather system, does not have communication, does not have the emergency system added to it.
Take it out?
When all of that is added, we project the suit weight to be something like 120 pounds. That contrasts with a 300-plus pound spacesuit that's out there today. Why can it do it? Because it's a flow-through system. It's not self-contained. It doesn't need tanks. It doesn't need fans. It doesn't need liquid-cooled garments. It doesn't. Well, of course, it needs smaller versions of that. But the mass is so low, and when you project it out with 38% Mars gravity, you're talking about something that is really super lightweight. And you could see the design of the neck dam completely keeps the separation together. I want to show you one thing before we skip to the Q suit. If I can get this slide back. You could go, if you guys could go to the very, very last slide if you can get it.
Feels good.
You go to the very end, and I wanted to show you. Okay, you're looking at the results of 3 days of testing with this system. And over the course of these 3 days of testing, what you're looking at is, for different colors, is the carbon dioxide measured inside the helmet under all different conditions. Okay? The black bar represents the carbon dioxide measured in an Apollo or shuttle EMU. Same level of carbon dioxide. So there's nothing migrating from that carbon dioxide atmosphere into the helmet. And we do that because we keep positive pressure in the helmet, so any flow that happens is flow from the helmet down to the torso. But more importantly, the design of the neck dam, if you can see it, really slam dunks any carbon dioxide from getting in there. Just to show you how effective this is, up here is the hypocapnia danger zone, and that's equivalent to 15 millimeters of mercury partial pressure. Here is a caution danger zone, equal to 7.5 millimeters of mercury PCO2. And I've seen plenty of spacesuit tests in my day where 7.5 millimeters of mercury is kind of like reached regularly. Now you're looking at what you have here. There is absolutely no danger, because people think, oh, you're going to put CO2 in a suit and what's going to happen? The answer is nothing's going to happen. You're going to have a lightweight super suit that can do things no other suit has ever done. So just wanted to let you know that, plus the weight, plus all the other features make this unique. So I want to now go from some of the primary features of the M33 to the MQ1. So if you look at the M33, you see filtration system, planetary protection, that basically is inherent in the design. But I told you before, the compressor blows in air through a filter, it filters air coming in, it filters air coming out. Now I want to show you the MQ1 suit. So the first thing to observe, while Elizabeth is going to push the button to pressurize, and it is pressurized, very slight pressure, and if you watch, once it's turned on, you're going to watch the suit start to bulge out a little bit. You can already see the legs starting to bulge out a little bit. There's a very slight pressure. And that keeps anything from the outside from getting in, just inherently. But I want you to turn around, if you would, Chelsea. So here you see the draw-in. These are built-in compressors, part of the suit system. They are drawing in air through super HEPA filters designed to stop anything larger than 1 micron. By reference, coronavirus bacteria is 1.25 microns or larger. And of course, you can unscrew these and put in any kind of filter. As the technology improves, you can different kind of filters, unscrew them and replace them. And the key is, look what at the bottom by the ankles. That's where the outflow is. So you're drawing in here. It comes up through the umbilicals at a high flow rate over your head, down into the suit, towards the bottom of the suit, migrates down toward the ankles, and goes out the ankles. So you want to turn around and make some, I don't know if people can hear you.
I don't know, can people hear me? Feels good in here, nice and cool.
So it's cool, it's lightweight, it's going to be inexpensive, and after Prada gets a hold of it, it's going to look like something they're going to run out to the store to get. So, I'm happy to entertain questions for a while. I know there's a reception afterwards, and we're going to have this on display out in the...
Probably maybe 2 or 3 questions, but you're going to be around here tomorrow.
We'll be around tomorrow. They're going to be out in the halls for you to ask questions one-on-one if you really want to get whatever question you want.
And as you're doing that, just remind you, people who are registered for the reception tonight, it's at the City View Room, which is at 1957 East Street. Remember Sputnik, 1957 East Street, which is go all the way down on the right. I mean, turn right, go all the way down to East Street, turn left. It's a few buildings down, top floor, rooftop. So see you then. But maybe 2 or 3 questions, and try to make them quick.
Sure. Go ahead.
Is this on? So I'm just kind of wondering, as we're talking about reducing CO2 emissions, are there any studies about how much CO2 would be emitted in making suits like this for 1 billion people to habitate Mars, and what is that going to do to climate change goals? I'm not being facetious. It's a serious, genuine concern and question.
You mean exposure to CO2 on a...
No, I mean manufacturing anything emits CO2, right? And
manufacturing. Oh, you're talking about sustainability. Is that what you're getting at?
Exactly. Yes. Yeah.
Oh, that's a good question. We're very lucky to get this guy just one up even made and prove the concept. As time goes on, materials will be very key. We have a MEC, module evolutionary approach to replace materials. Same thing with radiation. So it's hard to me to answer that question right now, as much as I'd love to do that. Thank you. More questions.
So my question was did the idea just pop into your mind, or were you inspired by anything?
Or just sorry, a little bit louder, please.
Okay.
Thank you.
Did the idea just pop into your mind, or were you inspired by the pandemic or anything?
Yes, the pandemic, of course, all of us had to find something to do with our time because we had a lot of it. We couldn't go anywhere. What can I say? I sat around driving myself nuts for 2 years. And fortunately, this was coming together. I have to say one thing that I think supersedes all of this, to give you an idea. I thought of this idea 30 years ago. And I wrote papers about it, and I kept on advancing the idea through what's called the Hypernet paradigm that I showed you, right? And then I kept taking it to conferences like this and presenting it. And after you do that enough years, you begin to get tired of your own voice, and you're saying, nobody's really listening. This sounds like a broken record, and oh, you're really putting CO2 into a suit? Oh, that's a cute idea. And you go ahead and do all this kind of thing, and then in the space of less than a year, you meet somebody who's just as inspired and interested in something, somebody who you needed to have to meet to make it happen, because you cannot do this alone. I would have gone on another 30 years. So first I met Gene Grace in the UK on a cruise ship of all things, and he said, I really like this, what you're talking about. Is there a way I can get involved? And he decided to pay for some of the development of this. But even if you decide to pay for some of the development, who's going to make it? Making a spacesuit is expensive. If you talk to NASA, you're talking 15, 20 million at a clip. So you can't do that. And that's when, just as coincidentally and miraculously, Cameron Smith came along. So let me tell you about Cameron. He builds his own spacesuits to jump out of balloons. He has a company called Pacific Spaceflight. He's making ballooning records that he's done. He also teaches anthropology. He's kind of a man of all. If you looked at his library in his room, his house, you would say, oh my God, this guy. So without meeting these two, none of it would have happened. And by meeting these two, it all happened like suddenly. Of course, all the ideas were percolating, but you need to be inspired. You need to be passionate about something. And if you're passionate about something, don't ever let anybody tell you you can't do it. And the most important thing is you have to understand that failing is your best friend. Sounds crazy. You have got to fail.
Hi, this is Michael Phillips from Johns Hopkins Applied Physics Lab. Thanks for that demonstration. That was really awesome. My question is about pressurizing these suits on Mars, and the atmospheric pressure is so low there. It seems like it won't require much pressure in the spacesuit to keep it at a higher pressure than the Martian atmosphere. But will you require tanks like you have there? How will you pressurize the suits there?
Well, we could pressurize CO2 tanks and make that part of the backpack, which would add weight. But if you have ultra high RPM compressors and lightweight compressors built into the material itself, it can pressurize the spacesuit. So yes, the fact that you have a lower atmospheric pressure is difficult. But if you can fly Ingenuity on Mars when everybody says you couldn't do it 10 years ago, you can certainly find a compressor that's going to pressurize that suit. So even if you run into problems like that, you just make the CO2 bottles part of the system. Once you pressurize the torso, it stays pressurized. The secret for thermal control is you let out a little bit at a time, and that takes, so you got to understand, the atmosphere of Mars is extremely dry and extremely cold. It will take metabolic heat away, as opposed to conventional suits, which recirculate, that you have to remove all the metabolic wastes, and that costs you tremendous mass. So even if you have to open up a valve to pulse out the CO2 that's been sitting there with all of your weights once every 10 minutes, it's still a solution. And of course, a key to all of this is a mathematical model. Now, we've built mathematical models of this, and they're being refined, but you don't do anything unless you build a model that shows how it works and actually does it before you start building. So there's lots of different, technologies and features you can get into. If you like coding, you can do coding and model a suit and model the system. Anyway, just you know what I'm saying, right?
Yes. Okay. So it would require vacuum pumps that can make a vacuum that's a lower pressure than the Martian atmosphere to pump air into your suit, is what it sounds like.
Yeah.
Yeah. Okay. Thank you.
You're welcome. More? Anybody else?
Yeah, can I just call one over here? What about the pressure differential from such a low pressure on Mars? You're going to have about 13 times less pressure outside than you do here. Is the suit going to puff up? Will you have to reinforce it?
No, it's all delta P. So in other words, if you can look on a vacuum, traditional suits operate in a vacuum and have 4 psi pressure above that. If you test this here, you have to test it at 19 psi. You want to make sure you don't do it with oxygen, because that's a recipe for a disaster, fire. So you don't do that. There's lots of ways to do it. And then finally, you do the last certification test you do is you do this in the Martian atmosphere, which means basically 10 millibars, hundredth of an atmosphere. You test in that environment. So that's the usual way you do this.
But you only have to pump it up to 4.
Yeah, right,
oh, okay.
Right, sure.
There's one more over here.
All right, just one more.
Can you use the suit on the moon as well? Can you make adjustments for it to work on the moon?
No, you can't. Well, let me take it back. If you wanted to pressurize the torso with another gas that you bring along, like nitrogen or any other gas or even oxygen, you could do it. So it would be much more complicated because the gravity it becomes an issue. The fact that you have to get these resources there, it just becomes more difficult. It's not that it's not worth doing, but why would we want to throw ourselves out there to the wolves that are trying to build 400-pound spacesuits and charge the US government $15 million at a click, when you don't have to do that? If you just have a kind of a SpaceX approach, you have an approach that this is unique, stick to what you know, and in 10 years, hopefully, this will be on the surface of Mars. Thank you. Thank you.
Thank you, Larry. That was spectacular.
Thank you, Chris.
Really
Thank you.
impressed.
Thank you.
Yeah,
And nobody died.
And nobody died. That was, I told him up front, nobody better die. So that was the #1 rule of this presentation.